Okay. Hi, everybody, and welcome to basically Chapter 9. We're starting Chapter 9. There are two components today, basically. We're going to introduce Chapter 9. And as I said in previous communication, I think we are ahead in our plans, basically, for this class. So that's why, actually, I focus a little bit on more basically trying to test and make sure that we have an understanding of what we're doing. And we did a quiz last Tuesday, and today we have another one. So the discussion actually today is a different kind of a quiz. It's a participation quiz. So I'd like to talk a little bit about that and how that works, because basically the only way you don't get a grade for it if you don't do it. So that's basically how that is different from the other one. And so we need to talk about that. So let's get going with Chapter 9. Okay, I need to get it open. Somewhere in the middle of the time, basically, I will take attendance, which is basically taking a picture of everything. And so I need the names to be clearly stated in there. I know Brandon is actually going by the B, but I need to know your names as they need to go basically on the system. So when I'm marking them, I mark them correctly. So so when I do the attendance, you're clear for it and it's not somebody else, okay? Okay, here is the file I need to share. Okay, so again, this is Chapter 9, and it's talking mainly about two objects, and that is the Moon and Mercury. And those are the two crater dwarfs that basically we'll be exploring. So something must happen to these two so that they get, at least they appear now to have more than anybody else in terms of craters, okay? And now, whatever happened to them must have happened to everybody else too. It's not like they're an exception to the rule, but for some reason it was preserved. Let's basically put it that way. Now, outside of the Earth, we humans, we have only been to another place outside of Earth, and that is the Moon. Okay. In 1994, I think, or 1993, I was in St. Louis exploring. And when Buzz Aldrin himself came in, and then as part of the American American, what is it? The Physics Teaching Association or some organization I was a member to at that time when I was in the Midwest. It's been a long time. Some of you probably were not born then. Anyway, I was there, and he came in and he gave a talk. The room was basically standing. I mean, there was no room for people to sit. Everybody, all the seats taken. And I was in the back, way back in the back there. And he was talking about his own personal experience, basically the minute he set his foot on the Moon. So that's really something that is, I know he passed away, I think last year or something like that, not too long ago anyway. But it was something that was completely different, like when you planet Earth, as far as we know, everything we learn about in the books, history, philosophy, anything that you can think of about any human who have ever lived in our lives, and most likely most of the people that we are going to ever meet in our lives, they have only been to this place, this Earth, and that's it. And it's very rare that you will find somebody like that who went to a different place outside of the Earth, and namely the Moon. So that's why it was an opportunity for me not to miss when I had the chance to go to and see him and listen to him and basically talking about his experience and so on and so forth. So when you get chances like this one in your life, try to take advantage of them, because probably they don't repeat, and things like this have significance. So the Moon is, like I said, was part of an intensive work in the past, where we tried to go to it, and we did actually go to it. We looked at its surface, at its geology, basically we studied it, and we discovered a lot of things about it that we'll talk about here. And actually, it's not just that. I mean, right now, I think the Trump administration has actually, I think they're planning, or they already have allocated funds or something like that, for a return to the moon. So this is not something that, as a matter of fact, let me stop sharing the screen. I need to share with you something from the news, since it's relevant to what we're talking about. Share this article in here. This appeared 6 days ago, basically, where this map of the moon was made. This looks kind of different. We have never seen a map of the moon that looks like this. And so basically what this is are all the minerals and basically the kind of stuff that is on the moon. So now it's presented as an opportunity for us to go basically mining. And if you need minerals, you need resources, the moon actually is very close and you have resources on it. So this map was made by the USGS, which is the United States, what is it? Geology or geography or something like that. Anyway, the people who are in charge of the map, US Department of something. Anyway, that's basically what the USGS came. And yeah, United States Geological Survey. And of course, that's really a something very, very important. And like I said, the administration itself, they're thinking to go back to it. And you will see actually in this chapter that we never basically stopped from going to it. It's not like it was in the 1960s and early 1970s, but we still are interested in exploring it. Now there is actually a talk about different planets, and the biggest one that is actually in the news, of course, is the planet Mars. And if we make it there, that will be another world that we will visit for the first time. I mean, all of them, we sent probes and we sent orbiters and we sent landers and things like that. But humans set foot on a different world other than Earth. It was actually the moon. That's it at this point. Okay. So some data that we need to know about the moon and Mercury, because this is some of the things that we will be discussing in terms of the properties of these two objects. In terms of mass, the Earth, of course, is far more massive than these two, okay? And to a point that the moon represents about 1/80th of a percent of what the Earth is. So relatively speaking, the moon is a big size compared to the Earth. If you take the Earth and divide it into 80 pieces, basically that's how much big the moon is in terms of mass. There are other objects, for example, other moons, and the first one that comes to mind, and it's always an example, is the moon Charon with Pluto, which actually the ratio is much bigger. I mean, Charon is much bigger than the moon as compared to Pluto, as the moon is compared to the Earth. So this is basically the size of the moon in terms of mass compared to the Earth. And compared to Mercury, the Earth is about 20 times bigger, basically. So that's another comparison that you have to have. In terms of radii, in terms of how basically physical size, the moon is about 2/7 of the Earth. Take the Earth and divide it into 7 pieces. The moon is about 2 times that number. And it's about, basically, roughly, it's about 1/3. And this was one of the ways, actually, early on, for astronomers in the time of the Greeks that were able to measure the size of the moon, basically, how big the moon is, the radius of the moon, and the distance the Earth to the moon, basically, based on other techniques using triangles. As long as you know the size of the Earth and you know that the Earth is about 3 times bigger, basically, or 7/2 times bigger, more precisely, then you can find its size. So that's basically one way of finding its size. And the way they determined that size was basically through the lunar eclipses. So that's one way of finding it. Now, when it comes to Jupiter, to Mercury, Mercury is bigger than the moon, actually. You have to take 2 pieces out of 5 to make the Earth. So let me click on this link in here. If I can get to it. I guess I have to, yeah. Okay, let me click to this link in here and stop sharing that screen and find the other. The reason why I want you to have a visual of what these numbers mean, because we can talk numbers all day long, but if we don't see them, we don't really understand them. So the link is actually in the PowerPoint, and I can send you that with the PowerPoint, which I probably should post. So this is basically, if this was the Earth, this is how much Mercury is, and this is how much the moon is. So if I put them inside basically one another, again, look, the moon and the ratio moon Mercury is not as big compared to, for example, either of them compared to the Earth. So that's what I meant earlier, but 7 pieces basically, 2 times 7 pieces, or 1/3 basically. So 3 moons basically will make the Earth, and actually a little bit more than 2 makes Mercury. I mean, 2 Mercury is slightly more, 2.5 Mercury basically will make the Earth. 3.5 the moon will make the Earth in terms of radius only, in terms of diameter basically. Okay, so this is an activity that I'm going to post for you guys to at least have visual, because it's always good to see things. Okay. So let me go back into the PowerPoint. So these are some of the physical properties that we have. One of the numbers that we always try to look at, of course, is the density. Density tells me what kind of stuff is in the planet, for example, or the moon. The moon is about 3.3 grams per cubic centimeters versus Mercury, which is the second one in terms of density after the Earth. So the Mercury is dense, meaning that it has a lot of, and because it's smaller, actually that means that probably it has a lot of metals in it and minerals in it, and that's exactly what happened. Versus the moon, which is deprived of its minerals and it's mainly basically silicate. So we'll talk about that. And also the other number to look for is the escape velocity. The escape velocity on Earth is 11.2. So on the moon, it's a lot less. So it takes less energy to escape the moon. So that's why when they send rockets to the moon, for example, they need a lot of energy to leave Earth. Once they land on the moon, because the mass, first of all, the lander usually are smaller than the actual orbiter, the one that orbits the moon. So the one that is actually returning to Earth and the one that left Earth. So the one that is the lander itself usually has less mass. So you don't need a lot of fuel in order to escape the moon. So it's almost 5 times less G there than it is on Earth. So that's why basically it's very, very easy to escape the moon, 2.4 kilometers per second. That explains also another problem for the moon, actually also Mercury. That's why they don't have atmosphere, because if their escape velocities were higher, so they can retain whatever atmosphere they have, but they don't. So whatever they had in the past, because they must have had, like everybody else, an atmosphere, but because of their low escape velocity also, they couldn't retain that atmosphere. The Mercury is slightly more massive, slightly more bigger. It has more gravity, more basically its escape velocity is higher. But the moon also has, they are both of them small. So that's the numbers basically. So the numbers, they tell a story behind them, and you need to know what that story is. Again, so these are some of the images of the moon. There are basically the so-called dark side, or the other side of the moon, the one that we don't see, this one, and the one that we see on regular, because the moon is tightly locked with the Earth, so we always see one face. So it's always, when it's spinning around its axis and it's going around, it's always giving us the same face basically as far as its motion. So there was a lot of interest in studying the moon from day on, basically, even when Mr. Galileo built his telescope in 1609, he pointed to the moon and he saw a lot of the features of the moon, the craters and basically the valleys and things like that, that are features of its surface. It was actually, people started talking about going to the moon. It was Mr. Yuri Kondratyev, who is a Russian, Russian, and also, in the old days, there was only Russia. What is the other? Seems to be the Soviet Union, but there is next to Russia now, and it's in war with it. Oh, I'm sorry, I lost the name in here. Forgot it. The one that there was a big political scandal a year ago or something. Do you guys remember the name? Anyway, doesn't matter. He proposed basically this technique in terms of going to the moon, and that was in 1919, way back before we actually started going and building rockets to go to the moon. So his idea is basically to leave the moon. So this is basically a 10-step process to leave the Earth. I'm sorry. After you basically you orbit the Earth, if you want to, or at some point you're going to go through stage 2, which is directly to the moon. Once you reach the moon, you're going to orbit the moon. At that point, you have two things going on. You have the orbiter and you have the lander. So here there is a separation between the two of them at this point, and then it lands on the moon. Now the orbiter continues to orbit the moon. This would continue going around the moon, waiting for the mission to be done, so that this comes in here and they meet together. And the word rendezvous, which is a French word basically for getting together, basically. That's what exactly it means. And so it's not just for dating, basically, purpose so you can do it. So they get together, they meet together. So that's when they join again one another. So in here, like I said, because the escape velocity on the moon is a lot less than that of the Earth, so it doesn't require a lot of fuel to leave the moon. So once you leave the moon, at this point, you're going to come back now. So initially, you're going to arrive in point 4 and then go around, the release in point 5, do whatever you need to do in point 6, then come back to point 7. And now you're orbiting back. This is point 8. And now you're going to accelerate toward the Earth. And at that point, once you reach the Earth somewhere, you're going to start slow down to start orbiting the Earth. And then after that, you're going to basically land. This is your final thing. So that's basically the schematic that was done. And indeed, that's basically the approach that taken into going into the moon. And it's still the most efficient way of economical way of going to the moon and coming back. So what kind of mission we had? This is basically, first of all, the Apollo program from 68, I'm sorry. Make this one. Okay, from 1968 to 1972. So the first few missions that we didn't land, and we flew with the humans, so we went there and looked at how things look around, and then we started landing from July 11th. That's when first landing on the moon. And then we continue going through the missions of going back to the moon. And we did a lot of things, basically. At some point, we collected a lot of material. So we'll talk about basically every mission. They have 3 basically objectives to meet. They bring stuff from the moon, especially rocks, in terms of studying them later on. And we gather a lot of materials toward these missions. And also, of course, we'll talk about the objectives basically in addition to that. Anyway, so this is an image of some of the things. Again, some of the missions in here. The first rickshaw, for example, on the moon was on January. I'm sorry, what am I talking about? Yeah, but January 1971. And then the rover, and then of course we left our footsteps in there. If you look very carefully in this picture, there are footsteps in here, and this is the rickshaw, and this is the flag that we left in there. So we did a lot of things in here, and again, these are some of the things that are the objectives of the lunar missions. Basically, we collected materials, about 400 kilograms. That's one of the things. We deployed basically experiment packages to check basically on the lunar conditions in terms of composition, in terms of any kind of motion, all kinds of things, any kind of seismic activity that was in there. So some of the times basically we deployed seismographs in there to study the surface, the subsurface of the moon itself, to see what kind of structure it has. And also the orbiting Apollos, basically they took pictures and they took detailed pictures of the surface of the moon. So there were so many things to do. And in this picture, for example, you have Jack Schmitt, who turned out to be actually a senator later on. He was basically studying the moon basically up close in there with the rocks, doing geological studies in there. The material we brought in here is still in the laboratories in Texas, and you can go basically and grab the materials, study them, see their composition, see what you need to look at. They are basically preserved in isolation so that they are not contaminated with the materials from the Earth, whether chemical processes or any other processes that we don't want them to be modified, because if somebody wants to study them, they want to know exactly how they are before they are altered. This is basically after the mission was over, we got a lot of them. Basically, they were sitting here and there. Nowadays, they're putting them in museums, basically, and enclosures so that they don't collect dust and basically deteriorate. Now, this is, like I said, this was not stopped. This is not the only basically missions we did. It's not like in the 70s and we stopped going. We went as far as 2013, as a matter of fact, by the Chinese. And we did, the United States actually did some experiments. Like, for example, this one is a different kind of, we usually talk about orbiters when we orbit a planet or a moon or something. We talk about landers when we send land in there, or we send a probe, so a device just that collects data and sends back data. But a lander, it's going to land, scan the area, and send data and communicate back and forth. This is an impactor, which is a different technique completely. So basically, what they did, they sent a rocket going at extreme high velocity and hitting the surface of the moon. And actually, they chose the South Pole because some earlier indication indicated that there may be ice in there. And sure enough, the material that flew back, now the orbiter went back through it and collected that dust basically that came from the collision, from the impact, and there was ice in there. There was water in there. So there is ice in on the moon itself, at least from the South Pole. And they were able to even estimate how much ice there is. So there is a lot of studies. So this study in here, an impactor, is a rare one that we did. And I don't know if there is any other one that we did on any other planet or any other moon, other than this one. We actually, in purpose, basically shut a device there just to get into to basically get a collision, to get the materials out of it so that we can study it. Okay. In the 2013 mission, which is the Chinese mission, they actually had a rover in there. They landed a rover in there. And the reason why I took this picture is for a very big reason. There is a lot of people there who claim or make false things about this thing of the moon is really a false claim and it can't be true. Look at the pictures, for example, they argue. Look at this picture, for example. You don't see the stars in there. How come we can see the stars? Well, this picture is taken during daytime, actually, believe it or not. And because the moon is lit, doesn't have an atmosphere, you don't see like you see the sky in here on Earth. And that's why you don't see the stars, because that's basically what you're looking at. Same thing in here. This is the Chinese. Let's say, assume, for example, the United States was doing some sort of a secret government thing, whatever those things claimants are saying. This is the Chinese now. This is their. So that's basically how this is not a fake thing. Then furthermore, not only the Chinese, but even the Indians now, they went there, and actually they went to not too long ago too, and Japanese, Europe. So this is, I mean, people sometimes when they think, especially now with this pandemic thing where a lot of people are sitting home, they will come up with all kinds of crazy nonsense stuff, and they argue based on images. This image is not that, and then the shadows are not exactly the same. Well, shadows, there is all kinds of effects to do it. One of them is the height. And I mean, when you take the physics of it, and if you put the physics in perspective in here, and the fact that there is no atmosphere on the planet itself, and the fact that all the lights basically are coming from the reflection on the surface of the moon, and if you allow for that, then everything is explained. Furthermore, from the previous link that I showed you, the curvature of the moon is a lot more than the curvature on the Earth because the radius of the Earth is a lot bigger. The Earth is bigger. So when you're standing on the Earth, the horizon looks like it's flatter than if you stand on the moon. So that's another fact that you're going to take on the when you're trying to if you are skeptical in trying to analyze these things. You have to be really fair and scientific before you go and start listening to those nonsense stuff. It is from a far away distance, about 370,000 kilometers, how the Earth looks like. So that's another reason why I like this picture in here. So again, these are some of the facts that were the studies that we did for the moon and things that we basically learned in terms of its geology, in terms of its geography. I mean, geology, I'm sorry. And because we did a lot of studies in there. And we learned a lot. So this is basically, in a nutshell, what we know about the moon right now in terms of its composition. First of all, its density is 3.3 grams per cubic centimeters versus that of the Earth. The Earth is 5.5 grams per cubic centimeters. So this one looks like it's depleted in iron and other minerals, and it has more silicate in its composition. That's why its density is less than that of the Earth. So that's one thing in there, okay? These studies, of course, were confirmed and by a lot of studies. One of them that did that actually was the seismometers that we left in there, trying to study the moon quakes, if you like to call them that way, although they're not too many, but when they do occur, you can collect the data from them and see the structure, basically, of the moon, see if it has a core, and if it does, how big it is. So it has basically doesn't have minerals as much as the Earth is. It doesn't have iron like the Earth does, or the nickel like the Earth does. And that explains now that 3.3 grams per cubic centimeter. So now we know. Remember this number, the density doesn't care how big an object is, how massive the object is. It cares only about the ratio of two things, mass over volume. So if the mass increases and with it the volume also increase, the density can stay the same, it doesn't change. So in order for you to have a more denser element, keep the volume the same and dump on it more and more mass, like for example, black holes. They're super dense actually to a point that you cannot believe. And or keep the mass the same, but shrink it. So when the volume goes down, then the material becomes denser. Minerals and metals, they are more dense than other compounds or other materials. So that's why that's an indicator for existence or lack of minerals. So that number is usually we go by. So, and again, it's confirmed. It's not just something that we looked at one number and we said, okay, that's it. So it's confirmed by the studies. Now, it's also from the studies that we looked at in terms of the rocks that were brought from the moon, it doesn't have a lot of water. Remember, water exists in abundance on Earth, and not just in the oceans, it exists actually in all kinds of, it exists in the air too, with a lot of it in the air too, as vapor. So basically, it is also depleted of water. So that's another thing that is also one of its properties in terms of composition. The moon also, if it has water, actually, it turns out to be too chemically bound to the rocks, and it's not much at all. So even that is not too much to really say that it was. Now, ice, water in the solid form exists. We know it exists in the at least the South Pole, and this is the study that I was talking about earlier, the impactor, when it came up. And there, we were able to basically estimate that this is a lot of basically ice. And 100-mile lake is not a lot compared to the Earth. I mean, Earth has far more water than what the moon does. But it should be good enough basically to take it and maybe if it's salty, make it remove the salt from it and use the salt for whatever chemistry you will need. Plus also you need the water for drinking. You're going to have a settlement in there on the moon. to do whatever studies in there or whatever stuff that you want to do. So there is water for that purpose. Furthermore, you can take the water and basically break it down into H2 by itself, basically hydrogen and oxygen, and use that as a fuel, for example, to go and leave the surface of the moon. Remember, the escape velocity is a lot less than that of the Earth, so you don't really need a lot of fuel to begin with. But if in case you need fuel, you have fuel in terms of water, which you run it through some chemical processes. You basically change you make you isolate the hydrogen basically by itself and the oxygen by itself and put them in two different tanks, and they are highly reactive though. So when you put them back to one another, basically when you try to burn the hydrogen, that's going to give you back water and a lot of energy basically. So this is a chemical reaction that is exothermic. So it's going to release a lot of energy, and that's basically what that's what propels the rocket to leave the moon. So that's basically in a nutshell the introduction to chapter 9 that I had in mind. And when we meet on Thursday, this has about 30, so we still have a long time to go before we finish. I just wanted to cover the first part, the first section of the chapter together. And let me take the attendance since I remember right now before I forgot. And then we'll talk about this quiz, and I'll let you start working on it. And actually, I will be here also to answer questions on it because, as I said, this is different. So I want to explain how different this is. So let me get to the quiz section first so that you guys see. It should have started by now, the quiz. Okay, I made it to start right during class time. But let me first of all start as if I am a student, because I want to have it from your vantage point so that you're looking at the exam as if I am a student. And student view. Okay, so let me go back to Canvas in there and share with you my student view of this thing. Okay, this is how the course looks like right now. So I'm going to go to assignments. And where is the new quiz? What happened to it? It's not what? Ah, here. Okay. So I'm going to click on it. A participation quiz, basically, you can only, if you do it, you're going to get a grade for it. Okay. Obviously, I want you to get the answers correct, okay, in order to get the grade. So here is the plan. Use the book. This is not a closed book exam. Use whatever reference you can go. So if you want to Google it, go and Google it. So there's no harm in it. If you want to communicate with one of your classmates, please do so. This is not, this is an open discussion quiz. The only way that you're going to fail this quiz if you don't do it. Okay? So that's basically how this is working. So you're going to go there and try to answer the question. If you still don't understand it, please send it to me. Tell me, hey, I don't know how is that question or understand it or something. I will go with it to everybody and say, okay, this is the one way, or post a question in there. If somebody willing to answer it, that would be great. The point I want to answer in here is that if you fail to go and put the answers on your answer sheet, you're not going to get grade for it. So I want you to be aware of these topics, basically. That's the point of this exercise. So I'm going to begin now as a student. Okay. This is not timed, so you have plenty of effort to do it, and you have a lot of time basically to answer these questions. You have until 9 p.m. though tomorrow. So if you have from now, this evening, tomorrow, it's out of 8, but you can have 13 points out of 8 because there are 2 points extra credit basically. They can end up with more than 100% in this one, and there is no harm in it. There is no problem with it. So the first question is, what are Earth's core and mantle made of? Explain how we know that. The key thing in here is probably the density, okay? And maybe the seismographs in here. But you can go and look at the book and see what that means, okay? So this is not, like I said, something that is trying to, this is something trying to teach you something. I want you to learn something out of it when you're done with this quiz. We're done with this part. You answer this in here. I come later on, make sure that you have answered. You touched on the key points, and it gives you the grade for it. Now, the second question, same thing. Describe the difference among primitive, igneous, sedimentary, and a metamorphic rock. Remember, there is one that stands out. The others are also all of the same root. The primitives are probably different, but the others rooted in here. And basically with the sedimentary, so basically, how are they different, okay? And where they came from. So again, this is question number 2. This is where you put the answer. So it's not gonna be on a separate piece of paper or somewhere else. So you're gonna write it. This one has a nice basically feature. So if I mistype something, it tells me that you typed it wrong. So if you think that you got something wrong in terms of spelling, please correct it first before you submit it, okay? So the next, what are the sources? What is the source of the Earth's magnetic field? Again, it has to do probably with the core itself and how the Earth is moving and how the core is turning and the temperature and things like that. So again, you're supposed to have that summarized in your own words, not in mine though. I don't want to see everybody's answer the same. So it has to be your own words, okay? But at the end, you need to understand what's going on in here. Same thing. I'm gonna go to next question. Describe 3 ways in which the presence of life has affected the composition of Earth's atmosphere. So we need 3 here, not just 1, 3. So you're going to look into how did life impact the atmosphere itself. Probably it was missing an element. That element came from some processes that happen in something, some plants or something, or some plant-like activities. And then that's one way. There is another layer that formed that did not exist before, for example. And there was an element that used to exist, for example, in abundance in the atmosphere, and now it doesn't exist as much because the plants basically took it as, or some life did something to it or something like that. So again, I'm hoping that these pointers help you, at least in review, going back to the chapter, going through the questions, reading the book, coming back, putting them, and you're looking for 3 here. So if I find 2, you didn't answer the question. If I find 1, you didn't answer the question. So it has to be 3 in here. Item 1, item 2, and item 3, okay? Briefly describe the greenhouse effect. Again, the greenhouse effect, how is radiation is absorbed from the sun. It has to do probably with the wavelengths and which wavelengths are absorbed, which ones are transmitted back, and which one reflects back on the surface, and so on and so forth. Again, what is that? How is it working in terms of the atmosphere? Okay. Why? This is question 6. Remember, it has 10 questions. The entire exam, quiz, 10 questions. You have plenty of time to work it out, and look at the sources, whatever you want to. But I need answers in here from each and every one of you. Why are there so many impact craters on our neighbor world, the moon, and so few on Earth? We just mentioned it. Maybe there is some stuff that has to do with the Earth surface, basically not keeping its stuff. I mean, for sure, I hope you guys don't think that it's because the Earth was spared the bombardment, but that's not the truth. But at least you think about it and you go back to the book, you talk to somebody, and ask one of your classmates, ask me, and see if we can come up with a consensus in here. If anybody asks me or asks Andrea, it has to go onto the discussion board. So the answer is not going to be privately to you only, okay? So it's going to go onto the discussion board. So Okay, but if you guys are communicating with one another, I don't care as long as you're going to put it in your own words. Okay. Which type of object would you like would likely cause more damage if struck near an urban area? A small metallic object or a large stony icy object? Think about it. A small metallic object would probably go straight through into the area and do its impact. A stony or icy object, probably something happened to it before it hits the ground. And if it happened near the city, since it's now a a large one, so probably it's going to survive most of its trip, but something will happen to it near the surface that could probably do damage. And compare the two damages, which one do you think is more damaging? Okay, that's your opinion now. Most likely you will not find this one in here. This should be synthesized. So I need you to read the book. There is an example in the book that follows this line, but this you cannot find. Probably you look for these keywords in the book, you will not find them. So you need to study the book and understand what's going on. So this is now synthesizing. This is now trying to come up with something that is the first 6 questions. You could find them straight from the book, basically. Question 8. Why is the decrease in Earth's ozone harmful to life? Again, there's probably a vague discussion in the book there, but I want your opinion about it based on what we know in terms of the ozone, what it does, and in terms of radiations and things like that. So I want you to think about it and come up with it. Now, question 9. This question is extra credit in here. I don't know if it shows that or not. What happened to the calculator in here? For some reason, I don't see the calculator. Oh, here is the calculator. Is this a calculator? Yes. Okay. So at this point, you're going to do a calculation. So if you need a calculator, you can have this calculator in here that can help you. I don't know if you saw it pop up on my computer or not. You guys see it or not?
Yes.
Okay, so basically there is a calculator that pops up, and probably you're going to do a multiplication in here or subtraction or division, because this one is a calculation actually. What fraction of Earth's volume is taken up by the core? So you need to look it up in the chapter in here and see what is the diameter of the core, okay? And versus the diameter of the Earth. Remember the volume, the formula for the volume is 4 pi times the radius cubed divided by 3. So basically, you may need to the calculations, but you might need to calculate the volume of the Earth, the volume of the moon, and divide the volume of the core divided, I'm sorry, not the moon, the core divided by the Earth, and tell me how much percentage do you think? So I need to see your answer in there, explaining basically the process and how you got your number. So this is for extra credit. This is worth 1 point, okay? So you get more points. So now if you do this, the first 8 questions, and you did them touching on the basis that I'm hoping you did, then you get 8 points plus this one. So you get 9 out of the basically 8. So let's move on to the next one. This is worth 2 points, okay? This is a little bit harder. That's why it's worth more points. And this is the last question in the quiz. Estimate the mass of the object that formed Meteor crater in Arizona. So Arizona, if you go and look into the book, it tells you basically the size roughly of the Meteor crater and what type it is probably, or you can guess what type it is. And we need to find its, based on its size, we need to find its volume. Based on its type, we're going to go and look into the density of that type and multiply the volume that we estimated based on the size. Basically, the volume is 4 pi, the radius cubed divided by 3, since we know its radius. Most likely in the book, it says it gives just a diameter. So the diameter, you have to divide it by 2. And then cube that number. That means multiply 3 times by itself. So basically, let's say, for example, it's I don't know. Let's say, for example, it's 35 meters, okay? I have to divide 35 meters by 2. That's a diameter. So it's telling me 17.5 meters. So what I do in here, I can use a power function in here, or I can multiply it by 17.5 and multiply it one more time by 17.5. So this is cubed. Now I have to multiply it by 4. And then I have to multiply it by pi. Here is pi, actually, multiplied by pi. And now I have to divide it. So this is the volume in cubic meters, okay? I don't know. Let's say, for example, the density is 5 grams per cubic centimeters. If it's 5 grams per centimeter, I need to find it in cubic meters. So because this volume I found is in cubic meters. So if it's 5 grams per cubic meters, that means per cubic centimeters, that means it's 5 kilograms per cubic centimeters. I'm sorry, it's 5,000 kilograms. So I have to multiply this number by 5,000. 5,000. If it's 5, I don't know if it's 5. So most likely it's not. Because if it's rock, most likely it would have disintegrated before hitting the earth. So it's not. Probably it's more metallic. So you need to find its density, which is higher than this one. I think they tell you in the book exactly what type of material is handled. Again, you can make some guesses what kind of things that could potentially have been. So you have 5,000 times this number. So this is the mass now. This is what? 1,000 million, 112 million kilograms. You don't need to worry about the extra numbers in there. It's about 112 million kilograms. Granted, I use 35 meters as the size of the meteor that we're talking about. It's probably not. The book probably gives you another one. So I want you to go and look at what the book is talking about when it comes to this meteor and basically find its volume. Once you find its volume, you multiply by its density. If you know what type it is, then you find its mass, because we're trying to find its mass, how big that is in terms of mass. So once you're done, you submit and you're done with this quiz. Okay. Now, if you come back and you realize that, oops, I made a mistake, you still have time, you can go back and fix it. So this is not, like I said, the point is trying to get you guys to go through the material again and get your participation grade for it. Hopefully everybody gets the credit for it. Does this, you guys understand what's going on, how this works? Okay, very good. So again, I want you to get started on it. We still have some time. I know in purpose so that you guys start right now on it, hopefully, and spend as much time as you need on it. And we will finish chapter 9, or we'll continue actually chapter 9 Tuesday when we meet again. Okay, any questions? No? I will try to make this recording available as soon as possible, because I know we have a lot of people who are not here. And I know, Alexis, yes, absolutely you will, okay? And there are only 2 people, okay? Alexis is asking me about her retake exam. So you will, okay? So I'll open it and I will let you know exactly when I'm going to open it, okay? Thank you, guys. If you have any question, please do ask it. If it's related to the quiz and you ask me or ask Andrea, I ask Andrea to forward that to me so that we have it in the discussion session. Thank you, guys. See you next week.
Thank you.
Bye-bye.